Hello, everybody. Developing safety-critical semiconductor according to the ISO 26262 standard is a quite complex and compute-intensive task. So automation of this process plays a key role in order to improve the productivity, but also increase the confidence in your safety methodology. So in the following talk, I will cover FMEDA creation and safety analysis, what we're going to do in terms of safety verification, and how we can drive then the safety-aware implementation. So let's have a brief look into some generic trends in the automotive market. So what we can see is that the Tier 1s and OEMs, or basically the whole automotive industry, is moving towards zonal controllers. And the zonal controllers will trigger, or triggering already, a chain reaction of developments for zonal controllers, for central compute SoCs, for new ADAS systems. And as you can imagine, since the goal of the zonal architecture is at the end to enable a higher level of autonomous driving, all these things are safety critical. In addition, what we can observe is that OEMs and Tier 1s are starting with SoC design, but also traditional semiconductor vendors coming eventually from the consumer market are entering the automotive market. So while the OEMs and Tier 1s are very advanced in terms of functional safety, so they have created and driven basically the standard, they have no experience in chip design. For the traditional semiconductor vendors from other segments, they are very advanced eventually in SoC design, but they are not familiar with functional safety. So that means both parties need, from a methodology point of view, some support. And overall, what we can see is that the functional safety requirements are increasing. New standards are currently in the creation, and I will talk in particular a little bit about a new safety format that we have created and introduced. So from a methodology point of view, the commonly used safety analysis tools are not connected with the IC design flows, and that's a problem. So that means at a system level or at a higher level, people are doing a safety analysis solely based on failure rates estimations. So, but if you go down to the SoC design, there are actually a lot of data that could be used for the safety analysis. And in order to do so, we have created a new level, what we called a detailed FMEDA analysis, which is a refined version of the architectural analysis. And so once you are done with the detailed FMEDA, usually you do a safety verification of your design. And the people that are doing the different levels of analysis or verification, as you can see, are mostly different engineers along this design flow. The results from a safety verification engineer can be then back annotated into the architectural FMEDA, and you can recalculate hardware safety metrics, which will hopefully result in a more accurate result. So let's talk about the first part. So how can we create an FMEDA to enable an early safety analysis? So Cadence has introduced a new safety platform, which is called MIDAS. And MIDAS enables an FMEDA-driven digital and analog safety design. And allows you to do an early safety analysis before any chip design has even started, so at a very high level. So in addition, we have this connection established, which I will cover later on in more detail, to our digital safety design and verification flow, where there are certain flows available that can be used for this task. And there's also a connection to our analog safety design and verification flow, mainly using legato reliability analysis. So this is the GUI of MIDAS, of our safety analysis tool. And with MIDAS, you can do this early safety analysis, but also you can do an architecture exploration, optimization, and I will come back to that also later on. MIDAS helps you to set failure mode, to assign safety mechanisms, and also do other things. And MIDAS can leverage native chip data for the detailed FMEDA in order to increase the accuracy. In addition, MIDAS supports a new format, which is called the Unified Safety Format, that allows you to capture the safety intent as part of your FMEDA. So if we have a closer look into the MIDAS platform and the flow, so you can have as input USF, but also the IC design. You can start with your architectural analysis, and once design becoming available, then you can extract from the IC design database, from our digital or analog flows, you can extract the design hierarchy and import it into the MIDAS safety platform. And obviously the FMEDA hierarchy and the IC design hierarchy could be very different. So there needs to be a design mapping done. And at the end, you move from an architectural FMEDA into a detailed FMEDA, and it could be an iterative process as you get to more accurate failure rates, diagnostic coverage values, and so forth. So let's go through the flow, how to set up an FMEDA in MIDAS. So you can, first of all, define your project. You can even select whether it's an industrial standard for safety or an automotive standard like the ISO 26262. You can define your ASIL level. You can even define at what level you would like to do this FMEDA. Is it IP level? Is it SoC level? Is it system level? That's the project setup. Within MIDAS, there's a base failure rate calculation engine that allows you to calculate the failure rate, and I will cover later on what is the input in order to do so. And this base failure rate calculation uses the IEC TR 62380 standard. Then you set up your FMEDA hierarchy, defining your parts and subparts. You define your failure modes, and you add your safety mechanisms. And at the end, once you're done with that, you can start already with your first failure analysis. You can create the metrics, reports, queries, rule checks, which I will also cover. So at the end, you have then eventually a table that shows you the single point fault metric for permanent faults, for transient faults, the latent faults, and also the PMHF as a full hardware safety metric. So let's go into a little bit into the details. Base failure rate. So the base failure rate is the overall failure rate that you calculate with this tool, which gets then distributed across all failure modes that you define in your FMEDA. So obviously, the more accurate your base failure rate calculation is, the more accurate will be also later on the overall failure um, um, analysis. And so the first thing that you need to enter is how many transistors or how many gates or flops are in the design. And this is usually the first thing that people are using as an estimation for failure rates. If there is already a design available, I click on the button, get the number from the design hierarchy and pull already this data directly from the chip design flow. Then you set up your custom mission profile, how this chip is used, in which application. You define your process technologies in which the chip is designed. You also enter your package information of that chip. And then you can already calculate the failure rate, the base failure rate for the chip. And so this is the formula from the standard that is behind this first tool. So now we have calculated the base failure rate. So once the design is becoming available, then I will import it into MIDAS. So this part here is your FMEDA hierarchy that you have defined. And so these names are simply block names. There could be also a hierarchical instance, and that's here shown on the left-hand side. So the minute you import your design, your chip design data, you have eventually a very different hierarchy. And what you need to do now is you have defined your failure modes, failure mode 1, 2, 3, and here are the parts, the subparts, and then you do a drag and drop of those RTL instances, for instance, to the failure mode, and it gets automatically mapped to those parts and subparts and also to the failure mode, and you see the number of gates, the flops, and if you would scroll over to the right, you will also see the area and everything. So that means once you have done this, FMEDA hierarchy, failure mode setup, then importing the design to you get the design hierarchy, do the mapping, then you leverage the chip data, you have already a more accurate calculation of your FMEDA. In addition, there's also a command line interface, and I mentioned in the beginning that we have created this unified safety format. So a lot of things that I'm doing in the GUI can be also done using the USF scripting language. But before we go to USF, let me just explain how you can optimize now your FMEDA accuracy. So the first step was actually to just use rough estimations, and you can see here your single point fault metric, your latent point fault metric, and so forth. So there is only estimations of this architectural FMEDA. So now we import the design hierarchy, and using the accurate transistor values, gates, and so forth, and recalculate the FMEDA, and you can see already that the single point fault matrix actually degrades a little bit because maybe the first estimations were a little bit too optimistic. But in this case, for the detailed FMEDA, you still do not use simulation-based diagnostic coverage values. And this is the third step. So we start now, after we have set up the FMEDA analysis with our safety verification, and then we get the accurate values for the diagnostic coverage, also for the safe faults, and use this data to recalculate the FMEDA analysis. And as you can see now, from here, 85.49% single point fault metrics, we improved it in just using more accurate values to 92.81%. So we would actually meet with that value already an ASIL B standard. So now we have seen we have overachieved ASIL B. And so the interesting thing is now, what will happen if I remove again a safety mechanism because a safety mechanism requires area in the silicon and also performance, and see whether we can still meet the ASIL B level. So we can create configurations with different failure modes, different safety mechanisms, and run the analysis again and compare the different configurations against each other and can pick the optimal setup in terms of failure modes of my design. And configurations have also the advantage that you do not change the actual design. So let's move now into the USF-based FMEDA. So it's the same flow as before, but in this case, it's not for the architectural FMEDA, it's for the detailed FMEDA. And as you can see here, if I would add in the command line set FMEDA, my FMEDA minus ASIL, I can already define my project as I did it using the GUI. I can assign various process technologies. I can calculate then the base failure rate with a certain command. I can create my safety, my FMEDA hierarchy using these commands. I can also create my failure modes with a specific command. I can do the mapping via an USF command. And I can then create my detailed FMEDA. At the end, I can generate a report also via command, and I can then, because it's now like a script, I can use certain queries. So that the advantage is of using USF, I can save afterwards this process as a USF script. And if you have, let's say, done one chip and you do a derivative of this chip, you can edit the USF script, load it into MIDAS again, and boom, the full FMEDA is available in your GUI and can be further optimized. So that means save USF and load USF allows you to capture the safety intent and reuse it again, which will help to improve the productivity for your next project. So now, since I have everything captured in a scripting language, I can, and the USF script is stored in the central database of MIDAS, I can use queries. And maybe I have already many FMEDA projects in my database. So if I use the command query USF, it will list how many FMEDA projects I have currently in my database. How many failure modes did I define for my project? There's another query with certain options, and it will list all the failure modes that I have defined for a specific project. If I want to know what is my safety metrics that I have calculated, there's another command, and it will show me in text format the whole hardware safety metrics of this project. And at the end, I can also verify using a so-called USF rule check whether everything it was entered correctly, and I did also a complete mapping of my RTL design and did not forget any block. And this command, check USF, will check that all failure rates of my failure modes will add up to 100%. So now we are done with the safety analysis. FMEDA is ready, and we can automatically generate a safety verification plan out of MIDAS that we can use in our digital verification process. And before I go into some details, let me just show you the whole flow. So we have MIDAS sitting at the top. And the next tool in the flow is now the Verisium Manager Safety, which is driving and automating the safety verification flow. Underneath Verisium, you can have either an analog mixed signal safety verification of your design or a pure digital safety verification of your design, or a mix. At the end, once you're done with your safety verification, you create a merged results view out of Verisium, And you can also generate reports that are showing the coverage, the verification coverage of your design. So that means Verisium is the tool to set up your safety verification and execute the verification, also optimize your tests and so forth. Then the analog mixed signal design verification can be also leveraged, and I will get back to that also a little bit later. And then you can do a results back annotation into MIDAS and visualize the results. So now if we go one step deeper into Verisium Manager Safety, so you get from MIDAS your fault specs, so which faults should be used for which failure mode, permanent faults, transient faults, single event upset, and so forth. You get a strobe list where to inject the faults, where to observe those injected faults. You get a test list from Verisium and a campaign configuration. Within Verisium, there's a simulation or verification flow set up using formal methods and also using Xcelium as a safety simulator to optimize the fault list. And then you have the results, which you back annotate again to MIDAS and further improve your tests and so forth. At the end, you get a coverage list out of Verisium that shows you exactly what is your percentage of test coverage for each and every failure mode. How many safe faults, how many dangerous detected faults, how many dangerous undetected faults, all these metrics you get out of Verisium. So that means Verisium is doing the fault campaign management across our simulation and formal engines in one single environment. You can back annotate your results. You can use traceability tools that have an interface to Verisium, and you can generate reports that you can use for your safety manual as a documentation. Jasper, our formal fault verification tool, is actually a tool that can identify which faults will propagate into a design, which faults cannot propagate into a design and can be tagged as a safe fault, which faults I can always detect, which faults I can never detect. So it applies a mathematical approach to classify faults. And the goal is that this huge fault list needs to be reduced as much as possible in order to simulate then later on the injected faults with Xcelium simulator. So it increases the safety verification performance. If we look now into the analog side, here we are talking about an automated fault identification and simulation, because we have here very different type of faults. We have maybe opens, shorts, high resistant, AC coupling, and so the IEEE P2427 has defined a list of defects that our ADE assembler tool can automatically inject and generate this fault list based on certain rules that you define in the tool. Once the defects are defined, you can simulate those defects using the Spectre simulator with two dedicated algorithms optimized for fault simulation. And then you can also back annotate those coverage values that you get out of this simulation into the MIDAS safety platform. So now we are done with the safety verification. We have met our safety goals, and we start now to implement the layout using our safety-aware implementation flow. And here the flow is based on Genus, our synthesis tool, Innovus, our place and route tool, and Conformal, our equivalence checking tool. And since you are defining certain safety mechanisms, and maybe one of the safety mechanisms could be a dual core lockstep architecture where you have two redundant cores, you want to make sure that our synthesis tool is not optimizing away one of those two cores. That's number one. And USF will drive the synthesis process and will tell the synthesis tool we have now a dual core lockstep architecture. In addition, we have Innovus. So Innovus needs to do the place and route, and USF will tell the tool how to place the two cores and also will guide the router that it is not routed across those cores, so a specific routing style is applied. Or if we use a triple mode redundancy, so different voting mechanisms, Innovus will make sure that those flops are placed in different physical areas. So that means the USF format is guiding the tools for a safety-aware implementation. Conformal is then checking that functionally what was implemented is really equivalent to what was described at the RTL level. And so that's an important task if you go through the full flow. So, and that brings me to the end of my presentation. So with our new safety platform, we provide an FMEDA-driven safety design for digital and analog mixed signal. MIDAS is the unified cockpit that basically is doing all the safety analysis, and USF is the scripting language that allows you to capture the safety intent. FMEDA is connected to our SoC verification flow for an automated safety-aware verification and implementation, and we have also a rule-based analog defect identification and simulation in this flow. And that brings me to the end of my talk.